So hello everyone, welcome back. So today's problem is mainly based on the idea of a little bit of kinetic theory of gases and mainly mechanics. Okay, so let's read the problem statement first. So we have a flat, thin, rectangular, homogeneous glass plate whose mass is m. It is suspended by two equal length light wires as shown in the figure. So this is the side view of the situation. Okay, and these are the two wires that they're talking about, and their lengths are given to be 2a, and this is the glass plate that hangs vertically. Now half of each side of the glass plate is symmetrically coated with a chemically active metal film whose mass can be ignored. Okay, so that is what they have depicted using these dots. So this is a small metal film that is chemically active. So on either side of the glass plate, half of it is covered by this special coat. Okay, as we can see from the top view of the situation, and from the side view it looks something like this, and the mass of this coat is something that we can ignore. Now the entire device is suspended vertically in an empty container, and chlorine gas with a pressure of P is introduced into the container. Okay, so now we have chlorine gas and the pressure of gas in the container is given to be P. Now assume the probability of each molecule reacting with a metal molecule is some Q, which is obviously less than 1, and Q is a constant within the time range under discussion. Now obviously there are chlorine molecules flying around in very large numbers inside the container, right? So let's say this blue dot is a chlorine molecule. So of these molecules that are going to be incident on this metal film, some of them are going to react and some of them are not going to react. So they're just saying that the probability that one of those molecules actually react with that metal plate is actually Q. There's a 1 minus Q probability that it does not react. Okay, so now the generated chloride remains on the glass plate. So basically they're saying that those chlorine atoms, and after they react with this metal plate, the product that is formed is some kind of a chloride, and it remains on the glass plate. Okay, so after reaction it does not rebound. So after reaction the chloride just remains on the glass plate. So that's what they're saying. So the linear dimensions of the entire device are shown in the figure. Okay, so basically everything required is just depicted in the diagram. Now when in equilibrium, the glass plate will rotate a small angle alpha around its central vertical axis. So we have to find alpha. Okay, so this is that central vertical axis. So they are saying it rotates about this axis. So from the top view, the entire glass plate, it rotates something like this, and they're saying this angle alpha is what we have to find. Okay guys, so give this problem a try, okay, and then check out the solution. Okay, another thing is that so basically 2b is the length of the glass plate, you could say, and a is basically the distance between this point and the point where the string is attached. Okay, so this length is a and this length is b. So first let's take the example of the case where we have some kind of a gas inside a cylindrical container, and the gas temperature is T, and let's say the pressure of the gas is P. And let's say there are n total gas molecules within the container. Let's say this is a piston that is holding the gas in place. Okay, and we are ignoring friction and all those things, and we are assuming that the gas is an ideal gas. Okay, so now the thing is, guys, when we derive this ideal gas relation, which is PV equals NKT, so here once again, P is the pressure of the gas within the container, V is the volume of the container, okay, N is the total molecules, and K is the Boltzmann constant, right, and T is the temperature of the gas within the container. Now here, when we go about deriving the ideal gas equation, one way we derive it is by finding the total force by the gas on the piston. And the way we calculate the force on the piston is by observing a molecule. So let's say this is a molecule of the gas. Okay, and obviously there will be a lot of molecules of gas that are flying around in different directions inside the container. Okay, and that number is around 10 to the power 24 in terms of order of magnitude. Now let's say one of those molecules is what I marked in the picture, and it has some approach velocity of v. Okay, so now when we derive the force on the piston, we state an assumption here, and that is the collision of these molecules with the piston is considered to be elastic. So basically after the gas molecule collides with the piston, it rebounds with the same velocity of v. And now the logic continues. So we say that every second n such molecules collide with the piston, and basically we try to figure out its momentum imparted every second. So if you observe on the molecule, the change in momentum is 2 mv in the leftward direction, and this momentum of 2 mv is imparted on the piston. Now we just try to figure out the total momentum imparted on the piston every second by all the molecules. So if I say that there are n molecules that are colliding with the piston every second, we'll find out the total momentum imparted to the piston, and we say that is the force that is applied by the gas on the piston. So we're not going to go into the derivation, but I want to explain the logic behind finding the force on the piston. So we start with the assumption that the collision is elastic. Okay, that's the reason why we are able to write this 2mv. If the collisions were not elastic, then this derivation would be wrong. This ideal gas relation of PV equal to NKT is assuming that the collisions are elastic. For a second, let's say if it was inelastic, after let's say this gas molecules collide with the piston, it comes to instantaneous rest. So basically, if the gas molecule came to rest, then the thing is the change in momentum would just become half, right? Finally, the momentum is 0, initial momentum is mv, so change is mv. So basically the momentum imparted on the piston would become mv in that situation, right? Which is basically half of the momentum imparted in the elastic collision case. So that's the logic we'll be using in this question. Now, on the glass plate, we'll be working with the assumption that the collisions are going to be elastic. Okay, so the gas molecules that are approaching the glass plate will collide with it and it will rebound. So the pressure imparted on the glass plate, we don't really have to think about it. It'll be the pressure of the gas itself. But when we talk about the coating, right, on the reactive metal part, okay, so let's just take the example of a molecule. Now, once this molecule collides with that metal, what happens is there's a probability of Q that it reacts with the metal. Okay, and if it reacts with the metal, the chloride ion formed is said to just remain on the glass plate and it does not rebound. So basically the collision of such a molecule is going to be inelastic, and the momentum imparted will be half the momentum imparted in the elastic case. Okay, which means all the molecules basically that react with the metal imparts a momentum which is 1/2 the momentum imparted because of the elastic collision. Okay, so that's basically the main idea. So now we are going to slightly modify this equation. So we'll send the volume to the other side, and we can say that the pressure, and we get P equals N by V times KT, and N by V is basically called the molecular density, or basically the number of molecules in a unit volume of the container, and multiplied by KT. Okay, so we can write P as just NKT. Okay, so now let's draw the top view of the diagram. Now the pressure of the gas was given to be P itself, right? So here, so basically the pressure exerted by the gas onto this glass plate will obviously be P, because here the collisions are of the gas molecules with the glass plate are considered to be just elastic. Now similarly the gas molecules will apply and will impart a uniform pressure on this part as well. Okay, so now the interesting part is with the metal, reactive metal. So P is just going to be NKT without a doubt. Okay, so now for this reactive metal case, let's say the pressure is P dash. Okay, now P dash is going to be slightly different. Now in order to compute P dash, we have to consider two possibilities. First is the chlorine molecules that react with the metal. So if they react, then that collision is like an inelastic collision like we discussed earlier. So let's say that the pressure because of that is P1 dash. Okay, this would be equal to, so it was given to us that the probability that it would react is Q. Okay, so basically NQ molecules have a probability of reacting with it, right? So if you just consider a unit volume of the gas present in the container, it will have N molecules, right? And of those N molecules, NQ has a probability of reacting with this metal plate. Okay, so the P1 dash is going to be N1 KT, but that's not it. We have to divide it with a factor of 2. Why? Because this collision is inelastic in its nature. So all the molecules will impart exactly half the momentum of those elastic collisions. So, and therefore the factor of half. Okay. Now, secondly, there will be chlorine atoms that don't react. So obviously the probability that they will react is Q, and Q is not equal to 1, which means there are some molecules that don't react with the metal. Okay, and those molecules will assume that after collision they'll just rebound just like in an elastic manner. So let's say their pressure contribution is P2 dash. So this will be 1 minus Q multiplied by N, again by the probability logic, times KT. Okay, and here we won't include the half factor because we'll assume the collisions to be elastic in this case. So the total pressure imparted P dash in this situation will be the sum of these two, right? And that, if you observe, is going to be 1 minus Q by 2 times NKT. Okay, and this is nothing but 1 minus Q by 2 multiplied by P. So this, if I write it like P minus delta P, so this P dash is going to be slightly less than P. Okay. Okay, so basically we figured out P dash is less than P. Okay, so if you observe about the center of mass, it will feel a counterclockwise torque. Okay, because the torques due to these two forces dominate the torques exerted on the metal plate. So it will feel a counterclockwise torque and it will rotate in the counterclockwise sense. Okay, so now the goal is to find out the torque due to these pressure forces. Now here, if you make a slight observation, you can make the process a bit easier. If you see that P dash is nothing but P minus delta P, right? So P, I can consider this as a sum of the pressure P, just like the pressure acting on the other parts, and minus a factor of delta P. So negative pressure will be considered as a suction force rather than the compressive force it actually is, right? So we can consider P dash as a superposition of P and minus delta P. Now the use of doing this is that because P is acting in all parts, we can say that the net torque due to P is 0. Okay, so in short, we'll just have to find the torque due to negative delta P, due to this delta P. So as we discussed earlier, this was more like a suction. So we'll apply a delta P force on this part, which will act like a suction. Okay, and here the delta P will be in this direction. Okay, now the thing is, as this pressure is uniform, meaning it's constant in magnitude, okay, we can apply the total force at the centroid of this part, okay, and we can just calculate the torque due to this main force. Okay, this we can only do if it is a uniform pressure variation. Okay, so now what is this total force? It will be the pressure delta P multiplied by the area of the exposed surface. Now the length of this part was B, and the length of this and the height of this part is C. So the area is BC. So basically this red force is going to be delta P multiplied by BC. And similarly here also it will be delta P multiplied by BC. Now if you observe, the net torque about the center of mass is going to be delta P multiplied by BC. Okay, we'll just times it by 2 because both of their torques just come out to be the same. Okay, multiplied by this distance, and that distance, if you observe, is just B by 2. This distance is B by 2. So we have to multiply this with B by 2, and this turns out to be delta P into B square C. Now delta P was equal to QP by 2. So we'll just put that in here as well. So this will be QB square C by 2 multiplied by P. So basically we figured out the net counterclockwise torque that the gas molecules apply on this glass plate. Okay. So now because of this, it will bend, it will rotate. From the top view, if you want to observe, the glass plate will rotate something like this. Okay, and this is the angle that they called alpha. This is the angle from the top view, right? And we have to calculate this. Okay, so now let's draw a slightly different diagram, including the tension forces as well. So now I'm going to draw a picture of the before and after situation. So these dotted lines, guys, these represent the top surface of the glass plate. Okay, so basically I'm talking about this part. Okay, and just to visualize, I'm not drawing the entire plate because here I want to visualize the tension forces. Okay, so I'm just drawing this line over here whose length is 2a. Okay, and that is this line basically. Okay, so we can give it a different color. The dotted lines indicate that this is the initial position. Okay, so now it will rotate in the counterclockwise sense as viewed from above. Okay, so I am saying, so let's say this end came over here and the other end went over there. Okay, and this is the final position of the rod. Okay, let's connect it. So this is string number 1 and this is string number 2. Now this angle is the angle alpha. Now this angle, guys, it is also given to us to be small. So we can use all the small angle approximations here, which means this part over here, this is just a very tiny arc. So we can replace it with a straight line whose length is the radius times the angle, right? So I am removing these red dots and just replacing it with a straight line, and the length of this part is going to be, okay, so this is the center of mass, guys. So the center of mass will remain in its place and the rod will rotate about the center of mass axis by an angle alpha. Now the length of this red line will be this length, which is a multiplied by alpha. Okay, so the length approximately is a multiplied by alpha. So this once again comes from the small angle approximation. Now the length of this string was given to be 2b. Now this angle we can take it to be beta, right? So if you observe, we can also use a small angle approximation for this part. This part also we can consider it like a tiny arc whose radius is 2b, and this angle is beta, and this is a tiny arc length of a alpha. So we can also write a alpha as 2b multiplied by beta. Okay, guys, so this wasn't 2b, this was actually 2a. Okay, so this will just be 2a. So from here, the relation between alpha and beta that we're obtaining is beta equals alpha by 2. So now the thing is, we figured out the torque because of the pressure forces. Okay, so now we have to find the restoring torque because of tension forces. So as you can see, this tension force, let's take for an example, it will have some component in the horizontal plane that will try to bring it back to the original position. So from the top view, if you want to observe, so let's say this is the original position of the rod. Okay, so now it has rotated by some angle like this. So there is a T parallel that is trying to, on both ends of the glass plate, that is trying to bring it back. So we want to find out that torque that is trying to bring it back. So let's mark the tension forces first. So this is tension T, and on the other string it will be in this direction. Okay, so now it'll be better if we break down this tension into two components. One component in the vertical plane, which let's just call it as TV, and one component in the horizontal plane, which let's just call it as TH. So the vertical component is basically opposite to gravity. Okay, so if I can just say 2TV equals mg. Okay, so basically if this angle is beta, so I'm drawing a side view of the string. Okay, so the tension is along this direction. Okay, so the component of tension in the horizontal plane, from this diagram we can see it is T sine beta, and the component in the vertical plane is T cos beta. Okay, so now we can once again use the small angle approximation. Cos beta is roughly equal to 1, so the vertical component is roughly T itself, so we can say T equals mg by 2. Okay, and the horizontal plane component is T sine beta, which is again roughly equal to T multiplied by beta. Okay, so now once we have the horizontal plane component, we can go back to the top view picture. This is the T parallel component, which is T beta, and similarly this is the T beta component acting on the other end. So this angle is alpha, this angle is also alpha. Now how do we find out the torque because of this T beta? So that will be nothing but this length A multiplied by T beta multiplied by this angle. Now this angle over here, guys, it is equal to, okay, so this angle is alpha. Now these two side lengths are A. So these two angles are pi by 2 minus alpha by 2, right? So these two angles, so this we can approximately once again just say it is pi by 2 because alpha is a small angle. So this angle we can basically say it's 90 degree. So the torque of tension, we can just say it is T beta multiplied by A. So this will be the contribution due to one of them. So there are two of them, so we'll multiply it with 2 as well. So this is going to be T multiplied by A multiplied by 2 beta, and 2 beta is just alpha. So it's going to be TA alpha. So now we'll just do torque balancing. T is just mg by 2. So mg by 2 multiplied by A alpha equals the torque of pressure forces, okay, which is Q B square C by 2 multiplied by P. Okay, so now let's solve for alpha. Alpha turns out to be equal to Q B square CP upon MGA. Okay, so this will be our final answer of this question. Okay, so that was basically it for this question, guys. If you have any doubts, you can comment down below. If you enjoyed the video, make sure to like, share and subscribe. And that's it. Thanks for watching.